Can you hear me? Yeah. Okay. I'm Preetal Shah, Product Manager for ISIL, Intel Storage Extraction Library, and SPDK. Together with me, I have Greg, who's standing there, the tech lead for ISIL, Intel Storage Extraction Library. So just to know, like, how many people here know about ISIL before I move into the agenda item? Just raise your hands. Just how many people know about ISIL? Okay. I know you guys know on the back, so we don't want to know. And okay. And how many are using ISIL today? Okay, there's just one hand and a few other hands over there. Okay, so I think then let me just go on to the next one. So what we're going to cover is what is ISIL in brief. We're going to talk about just giving what we've added as features in ISIL since last year and what is coming on the roadmap in the next year. We're going to go in, do a deep dive about ISIL compression. We're going to talk about DPDK Framework and how we actually integrate it. And we're going to give an example. I think Daniel touched on it, Paul touched on it yesterday, the SPDK BDEV Crypto POC, quickly touch on it. And then we're going to talk about possible examples which can be done and the community members can help in terms of creating SPDK BDEVs. Okay. So what is Intel Storage Extraction Library? I'm just going to go. Intel Storage Extraction Library comprises of highly optimized storage algorithms through hand-coded assembly, and it helps you to maximize storage throughput, efficiency, as well as resiliency, and it actually helps you even in terms of minimizing the disk space usage. Storage application developers can go in and use this and it gets better performance and efficiency on Intel platforms, as well as it can be used on other architectures too. It is actually using a single API, you can use it on past, present, and future architectures, and it helps in reducing the time to market in terms of using these storage libraries. It is operating system agnostic. We've tested it on Windows, FreeBSD, as well as Linux platforms. And last but not the least, it's free, open source, and BSD license. So there's a lot of people out there using it, which we don't even know about at times because of the licensing. So we have just created, it comprises of hundreds of functions. We've kind of categorized them into buckets here just to show you up there. So the first one, which we support in terms of the functions we support, are compression functions. We support deflate, fast deflate, and fast inflate. And Greg's going to go deeper into it, so I'm not going to spend more time on that. We have hashing functions, multi-buffer hashing, multi-hashing, and we also have rolling hash. In terms of crypto, we support block ciphers, 128 and 256 bits. Data protection, we have RAID 5, RAID 6, and we've also added erasure coding, Reed-Solomon erasure coding, which helps you to minimize the data footprint on storage platforms. And data integrity, we support CRCs to detect the data transmission errors, while transmitting data, and 16-bit, 32-bit, as well as 64-bit. Along with all these functions, ISIL actually has been integrated into a lot of open source libraries. Just to name a few, there's HDFS actually has ISIL erasure coding already supported through HDFS. We have Spark SQL, Swift. Ceph also has ISIL compression and erasure coding integrated into it. The last year, GATK, which is the Genomic Analysis Toolkit, Development Toolkit, they actually went in and integrated ISIL compression. And what they've seen is, in terms of compression, 2.7x improvement in terms of compressing the genomics data, as well as 2x improvement in decompression if they use ISIL library within the GATK. And one more integration, which we're going to go a little bit deeper into, related to the crypto BDEV, but is happening right now and will be released by the end of this month, is DPDK Framework. So ISIL compression is getting integrated into DPDK Framework using a single API. You can use either software-based ISIL integration, and in future you'll be able to use in hardware acceleration too, or QAT for doing compression. But it's going to be in future releases, but ISL compression is getting integrated by end of May. And apart from this, there are hundreds of other proprietary products which probably have ISL using into it. We just can't name all of them in here. Okay, so now I'm just going to talk about what we have integrated in the last year and what we've added into the library. So we do time to time, we do architecture updates, and with Skylake, we added in fast deflate compression improvements, and we added AVX 512 version of RAID 5 and RAID 6, as well as we did improvements in terms of multi-buffer hashing. Okay. And just to point out a couple of new functions we've added in is stitch CRC plus copy in data integrity, AES GCM as block ciphers, and we open sourced and we added rolling hash in last year. And in terms of compression, we added in 3 different new levels for fully dynamic, 1, 2, and 3. We added standard directory support, as well as we went in and added zlib format support. And further, in terms of performance, we see much better performance from what we saw in level 0 static Huffman. So I think with said that, let me go into what we plan to do in terms of next year. We're going to go in, and in this year, we're going to, in the next release, no, sorry. OK, I'm combining SPDK. ISL 2.24 release, we're going to go in and add decompression improvements related to multi-byte decode. We are also going in, and as Icelake comes in, we're going to add all the architecture updates or improvements in terms of compression, CRC, as well as crypto block ciphers. OK, I think this is the part I was going to cover, and I was going to hand over to Greg to go into do a deeper dive on compression.
Thanks, Preetal. Thanks. So I'm Greg Tucker. I'm the ISL tech lead, as Preetal said. I was going to talk specifically about compression. In the effort of time, because as Preetal said, there's over 100 functions in ISL, and each function has 3 to 4 different architecture versions, typically. And also, we've done a lot of recent updates to compression, and we made some improvements in the last 2 releases. And it's also, compression is one of the most computationally intensive storage algorithms. So it's a big pain point, and that's one of the reasons why we've put some recent effort into our compression offerings. So with that, what we have, whoop, wrong way. Let me find the right button. The big green one. OK, I found it. So what we have in ISL compression is a fast deflate, we call. We stuck to deflate because it's a ubiquitous standard. It's built into other standards. It's been around a long time. It's not changing, and it's lossless. And so it's good for storage. So what we've done is completely redone a deflate, but concentrate on the low level. What we have is level 0 through 3. And the purpose is because for inline storage, we want to go fast, and there's a certain minimum throughput you have to hit in order to be inline and do compression on the fly. So we concentrated on these low levels, and stuck to deflate because it's a ubiquitous standard, and there's lots of other options for it. What we had last year was just 0. We called it 0 because it was really static Huffman compression. And we were very happy with what we had at the time, but since then we made a number of improvements both to compression ratio and to throughput. I think back a year ago, we had a level 0, and it was getting about 12 cycles per byte. And since then, we've added the level 1, which is fully dynamic Huffman, so we've increased the compression ratios to be roughly similar to zlib, low-level zlib. But we're now on the order of 6 to 7 cycles per byte. This is Celestia standard. So we made a lot of improvements, both to compression ratio and to throughput. And this is for levels 0 through 3. And then we also have a decompression, and it works on any level, any deflate stream, and that we can decompress. So these recent improvements have put us into sort of a new, opened up a lot of opportunity for where we can apply our decompression. Although we built it specifically for storage cases, and we've added features into it over time that we got feedback from other storage customers. So what we have is zlib. It's and we've taken the first 4 levels and really shifted it this way to be 5 to 6 times faster than zlib. So in compression, there's always this trade-off between compression ratio and throughput. So there's a trade-off. The better compression, you have to try harder, and it's slower. But we've improved this so much that it's actually, it puts us in a new category. We're even faster than some of these other more modern standards, Brotli and Z standard. And so we're kind of in this upper triangle or polygon of goodness up there where no one else plays. So we're similar compression ratio of zlib, low-level zlib, Z-standard Brotli, but much faster. And we're roughly at the speed of built-for-speed protocols, such as Snappy and LZ4, but they have limits on what they can do for compression ratios, a much better compression ratio. So this has helped us be perfect for storage, inline storage. We can do hundreds of megabytes per second on a single core. And like I said, opened up a lot of opportunities, and not just in storage. So, and in decompression, we also have a Deflate compatible decompression, and it's roughly 2x faster than zlib. And it also has the property that the higher the compression ratio you compress the stream at, the faster it goes. And like Preetal said, we're currently making a multi-byte decompression. So that'll work by consuming multiple symbols at a time and decompressing them together. So there's going to be even more. It's going to be even faster in the next release, and that's going to come up in the next month or so. So some of these dots will go off the chart, we think. So now the compression is one of the it's actually the highest computationally intense algorithms. Even though we've got it down to single-digit cycles per byte, we've done a lot of work with all the other parts, and so we've pushed all of them to be single cycle or fractional cycles per byte. So compression is one where it's good to also have options, and that being a high cycles per byte kind of algorithm, it might be considered to have hardware acceleration. But there's always trade-offs between hardware acceleration and doing things on the core. QAT is an offering from Intel that does hardware compression, and it's got tremendous throughputs. But with any offload, it depends on how far it is from the core. There's trade-offs on latency with being on the core. And there's other options too, but you got to keep this in consideration, I guess. So, but thus, DPDK, the SPDK is built on, it has already got this abstraction for QAT. And so what they currently have is what they call CryptoDev, and it does a single API that you can offload some block ciphers to, and you can either do the same API to QAT as an asynchronous offload, or it can run the same algorithms in the optimized software library. But what's new, they just added a new interface they called CompressDev. It's very similar to the CryptoDev, but it does deflate compression. And so they plan a number of cold mode drivers for it, one with QAT and ISAL and zlib. And the first PMD that get integrated, and just integrated last Friday into DPDK mainline, this ISAL PMD that does software compression. And, but it'll be quickly followed on by the QAT and zlib and probably others. So, and you don't have to wait. As Paul mentioned before, there's already work in progress for a block dev that uses the DPD CryptoDev, and it can target either the QAT offload or a soft load. And so next, I just want to put a few examples of, we think ISAL and SPDK are perfect together, both user space libraries, and these new block devs are the perfect place to put these storage algorithms, the part that touches data. And because it stacks on top of other BDEVs, you can have the same backends or any backend, and then do your storage algorithm in this virtual BDEV. And some examples: encryption, compression, dedupe, analytics. I mean, I'm sure there's just tons of things. And ISAL, we've built up storage algorithms for storage customers, and so we think perfect place to put to integrate ISAL. So you might imagine if you had a BDEV that did a cryptographic hash on every block that goes through it, and many storage applications do this, and they could do this either for, it could be part of a dedupe a block, or data integrity, or data placement, I've even seen. But the computationally intense part, the hashing, the part that touches every byte, we've been driving down these cycles per byte to be, and like you can see, we can do most of these hashes in either single cycle or a fractional cycle per byte. So if you want to hit a million IOPS, that's really billions of bytes per second you have to stream through this. And so we can do gigabytes per second throughput on a single core. So it's not necessarily the bottleneck of hashing every block. So maybe it's more difficult. Well, RAID also, not difficult to imagine a BDEV that's RAID and does RAID 5, RAID 6. But the parity calculation part, we can do it, over to tens of gigabytes per second. So it's certainly not going to be the bottleneck in the implementation of a RAID, RAID 5, RAID 6 BDEV. Another example. So erasure code, maybe it's more difficult to imagine erasure code BDEV. It would talk to other systems, but certainly we can also do this fractional cycles per byte, which is over 10 gigabytes per second. It's not going. I don't imagine it being a bottleneck. So compression maybe doesn't make sense to put in a BDEV. Some people do compression of the block layer, but there's probably many entry points in an application where you can do compression either directly at the application, in a database. It's built into some databases. In a file system, we might do an extent at a time. But since these recent improvements, hundreds of gigabytes per second, we could hit gigabyte per second in maybe 3 cores. So, it's not necessarily, even in software, to be a limitation. And then there's, there's different hardware offloads that are available also. So I think you get the point. Encrypt, we can do block ciphers at fractional cycles per byte. That's gigabytes per second. Again, it's not necessarily performance limiting. So that's all. I guess the summary is, don't be afraid to add these. I think it's inevitable that some of these storage algorithms will be integrated with SPDK, and we've got the throughput. And even data compression, not necessarily a huge obstacle. You've got options with software or hardware acceleration. And VBDEVs is a great place to put this. ICL algorithms. So if you have questions, please visit our wiki, or you can, if you have questions about the other software ICL algorithms, and you can ask me now or stop me later in the hall.
So the question is, earlier I asked a question about AES, XTS, and people said, well, it's not in DPDK yet. But then it's not obvious, why is SPDK not based on this instead of DPDK, since you seem to be further ahead and maybe even more performant? Why would SPDK not take all this as their base?
Yeah, AES XTS is a very typical storage algorithm, block cipher, and used lots of disk encryption. And that's why we added AES XTS. It was one of the first block ciphers we put in ISL because of that. So the first applications for CryptoDev were for networking, because it's DPDK. So they have what they call an IPsec library. It was for IPsec applications. And so they put different block ciphers that are more typical in IP encryption. And XTS is not one of them. So when they made it, they used existing ones that are already available in the CryptoDev. That was built for networking protocols. But they have plans to add XTS when they get it in QAT. I think it's already available in QAT, but it's not in their CryptoDev yet. And we already have it, and it'll be available in their libraries. The IPsec multi-buffer library too. And then it's going to be a feature.
So just to add a little bit to what Greg said, right? So when you look at it, we did have discussions about, okay, what we wanted to do because of, okay, we had certain things in ISL that weren't yet in the DPDK framework, but did we really want to go and have separate modules, right? Or did we want to ultimately try to have a single API that we wrote to that would go off and do the right thing underneath the covers? And so what we opted to do was, for now, we're going to program to the DPDK framework and actually take software from ISL to do things like AES, XTS, and actually make it part of the CryptoDev framework, right? Yes, yeah, exactly. So it was really more about trying to keep a simpler set of APIs that we're writing to. But, ultimately, we could make decisions to go down a different path if it's what best suits the project.
A question over here.
Hi, I didn't get this. Does the library use the hardware acceleration that's available on DI, or how does that work?
No, ISL is a completely software-only library. So we're only using instruction sets on the CPUs.
So is it possible to do this in the future, to enable use of hardware acceleration within the library, or it has to be done by the user?
Well, we plan to work with other hardware acceleration like QAT, so that there's similar ways, or sometimes the same function, like Deflate. They have a Deflate, we have a Deflate. So to give the customers options about doing it in hardware offload or doing it in software. And as I said, sometimes it makes sense to do it one, sometimes it makes sense to do it in, or both, depends upon your needs. So yeah, and the DPDK framework is one just good place to have a common API. But sometimes you don't, it's better not to do a synchronous, if you have a synchronous version, it's better just to do it in place. So maybe in that case, you just call ISL functions. In other cases, you could use the same interface and have one binary, and it runs sometimes on QAT or other hardware offload, and sometimes in software. But ICL charter is to make, derive the best on software. So we're going to keep making improvements on the software.
Yeah, do you also have performance numbers, the throughput difference between using ISA-L and using hardware acceleration?
And using which one?
And hardware acceleration.
Oh, I don't have QAT numbers.
We have them, we just don't have them in this
Yeah.
slide deck. Yeah.
Yeah. I mean, it really depends. But their throughput on their deflate improvement performance is quite good. I think in new architectures, they're approaching 100 gigabits per second or something of deflate.
Thank you.
And one thing just to point out, right, we've talked about the DPDK framework a little bit in different places. I think it's important just to remember that DPDK is an open source project. It's part of a foundation, right? So there's all kinds of hardware accelerators that can actually be supported within the DPDK framework. You hear us talking obviously about the ones Intel provides, but the project itself is broader than that.
Hey, quick question. I saw a slide where he showed there was a SHA-1 plus murmur. Is it like a multi-level hashing or?
Yeah, that was a specific request for a customer that it actually stitches, I think, SHA-1 and murmur.
So it's basically hash to hash, or?
It does both. It does a SHA-1 hash and a murmur. And so one is very vector oriented and one is very non-vector. So they stitch very well. So we were actually able to get the performance. On some architectures, we got the murmur for free, actually. So it runs just as fast on some architectures. And then you get both. So the cryptographic hash and murmur is not really a cryptographic hash.
Right.
You get them both together, and it's faster than doing them, one and then the other. So we have a lot of things like that where we've built ISA-L up from feedback from storage customers. So they give us feedback. We could use it, except it doesn't have this feature. So we work on that. We add that feature. And these are some of the unique things we have in ISA-L. There's a lot of niche things that are just for storage. And then some have broad applications we found, like genomics, with the compression. And there's other, streaming, applications people do it. But primarily, we want to make the best, available for storage applications.
All right, thanks.
Hello. Yeah, hi Greg. I think you or Preetal already covered this, but can you just highlight what are the compression new additions since the last year, like how much it has changed? We are kind of interested in compression, decompression, so if you can just highlight in your, if what has changed since last year, that would be nice.
Yeah, sure. So I mentioned a couple of the ones where performance increases. We've added multiple levels, so the higher compression ratios. We've added features too, like dictionary support. So you can, it's a part of zlib. We've dictionary support. Let me think. Yeah, I mean, there's been a number of things we've added, but we've concentrated on the performance improvements. And we had, over the last year, we've had a number of successes getting it, from down to single-digit cycles per byte. But you have to look through the list. I mean, there's probably other features I'm forgetting. But primarily the improvements for the last year are the multiple levels, fully dynamic Huffman compression, and performance improvements, of course.
All right, thanks, Greg.
Mm-hmm.
And thanks, Preetal. All right, so